Hey, shut up. I have a question. Can y'all hear me? I don't know if y'all can hear me. But I was wondering if y'all have like a group chat, like a what's it called? Like the group me's for math. No? Yes.
Hello, pre-calculus class. Just doing a sound check. Is the voice coming across clear?
Yes.
sir.
Thank you. That's always good to know. I'm sure I'm beating a dead horse where that's concerned, but that's it's important for you to hear me. Okay. I will have some information for you about the test. I'll probably post that tomorrow. Like I said before, the first test will be a WebAssign test, and so you will treat it as any test. That is, it'll be a timed assessment, and I'll give you some instructions about what I want you to do as far as the test is concerned. So that should keep everybody at ease. And just remember that the material that we complete today will stop the material for test number 1. And then, of course, anything that we cover next week will be on the next test. The week of the test, I don't introduce any new material. I know if you've taken summer school, that's not the case. There's no time. You introduced to a topic and it seems like the next day you have a test on it, but the material will stop today. So I think you're going to enjoy the topics today. Again, more review, one-to-one functions, inverses, and also just a short lecture on the quadratic function, which basically summarizes all of the ideas that we've done with the quadratic equation. So I think you'll find that the work that we do with the quadratic function is very useful, and it will help to bring everything together, assimilate all the ideas that you know about quadratic equations. So first, what I want to do is I want to share my screen so we can talk a little bit about one-to-one functions and just get some basic ideas down, some definitions. So when we look at this and we think about what we need to do, our friends are basically the quadratic functions and the one-to-one functions. But we know every function doesn't have these nice qualities. But when we do encounter them, we want to be able to react in a way that provides some understanding. Okay, so also in your WebAssign, that you might have examples that say, oh, a graphing calculator would be useful, or verify with a graphing calculator. Just ignore that. That's always put into newer textbooks as a technology plug, but you don't need that. That just ignore it. You can do the problems the way I teach you how to do them. So again, you can always use your fancy technology to try out things and test things. There's nothing wrong with that, but don't feel like you have to use it for the problem, because on the test, I will test you on the items that I have introduced and that utilize the paper and pencil and the symbolic computation. Now, what we want to start out with, I just got a few definitions that I want to go through. Then I'm going to do a very straightforward example and then expand upon that to summarize the one-to-one and inverses, and then move on to the quadratic. Now, remember back in college algebra, you had this funny test, just like for the definition of a function. It was called the horizontal line test. Now, the thing is that the problem would say, well, graph the function so you can determine whether or not it's one-to-one. Well, that's a circular argument. You can't graph a function if you don't understand it. So we're really not going to do that. There'll be some problems on WebAssign that will talk about a representation of a function. And you'll look at it and say, does this represent a one-to-one function? And then you can think about the horizontal line test. But that in no way is a proof that a function is one-to-one. So I want you to kind of discard that. We have the definition of a function, again, which kind of discards the vertical line test, even though that's not as bad as the one we just mentioned. Okay, so how do we know when a function's one-to-one? Well, here's a standard definition. A function f is one-to-one if and only if we have the following condition. If we have two elements in the range that are equal, that is f of a equals f of b, and you can use any letters you like, ladies and gentlemen. A and b are just convenient. This will imply that a equals b. Basically what that's saying is that if you have two elements in the range that are equal, it must be the case that the inputs were equal. And that's an algorithm that we will use to show that a function's one-to-one. Now, some students like it written this way, which is fine, but we're usually going to stick to this. So you can say different inputs, different outputs. So if A doesn't equal B as inputs, then f of A doesn't equal f of B. So remember, a one-to-one function is a function. It just has this special property. And you might say to yourself, this is extremely restrictive. So like even functions and odd functions, most functions do not fall into this category. But I want us to be able to read this and understand what it means. Now, what does this imply? Well, basically, ladies and gentlemen, there's not a whole lot to this. If a function is one-to-one, then it defines an inverse function. Now, what we're going to use is a standard notation, and you're going to think, well, you know, f to the superscript minus 1. What we do in this case is we think of 2 to the minus 1 as being 1/2 in the sense that it's the multiplicative inverse of 2. Well, we're not going to think about this as reciprocating f. We're just going to think that this means or symbolizes inverse function. So I know at first when you saw this symbol in college algebra, you probably thought, well, that's an odd notation. Well, it has become universal. Now, the idea is this. We say that f inverse defines the reverse path. So as you move from the domain of f to its range, the range of f is now the new domain of f inverse. And then f inverse moves the reverse path from the range of f back to the domain of f. So what we're seeing here is that this is kind of a crazy situation. It's just a flip-flop. That is, the domain of the inverse function is the range of f. And therefore, the range of the inverse function is the domain of f. So there's nothing new to have to figure out. So you might be thinking a one-to-one function already tells you what the reverse path is. It just might be nice to write it down. And that's really what we do. So there's nothing new. If you figure out the range and domain of f, you automatically know the range and domain of f inverse. Easy. Now, I want to just go over some particulars that have become convention. Now, if you say y equals f of x, you can think of flipping it around to say that x equals f inverse of y. Now, this notation is what we like when we are trying to keep the x's and the y's separate. And this is actually quite valued when you're dealing with inverse functions in trigonometry or hyperbolic inverse functions that you do in calculus. So we're thinking it's good to stick to this when we're maybe doing that, as I just suggested, or maybe we're in a physics class or an engineering class, and it makes sense to stick with these letters because they represent quantities that we want to keep separate. And I'm going to do an example of that to show you what I'm talking about. So one thing that we do that varies a little bit from this is the following. In order to utilize certain properties about the path and its reverse path, we will sometimes just go ahead and elect to use the same independent variable for each function. Now you're thinking, wow, that's kind of confusing. I mean, I kind of like this because I keep the x's and the y's separate, but there is some utility for thinking about it this way. Now, let me just go over to tie in what we talked about with compositions. When we compose f and its inverse in either order, for instance here, F composed with F inverse of X, where X is in the domain of F inverse, we know that this is just F of F inverse of X using the definition of the composition. But since these reverse each other, the input equals the output. Again, using the same letter. Likewise, in the other order, F inverse composed with F of X, that is F inverse of F of X, is the same. The input equals the output, where again, in this case, X would be in the domain. So what we're seeing here is that the composition in these cases is the identity function. Input equals output. You know, the function F of X equal X, that is Y equal X, is the identity function. Input equals output. So this basically showcases a situation where it may be convenient to use the same independent variable. Now, another reason for that, and we will do this when we talk about some of our examples shortly in the next couple of examples, excuse me, we can think about the fact of the reverse path. We talk about a function as being a set of ordered pairs. Well, if AB is an element of F and it's 1-to-1, then you can interchange the A and the B and write B A. That's an element of the inverse function. So if you truly have a 1-to-1 function, you can always say this. Just flip the coordinates. Now, what this means is that graphically, F and F inverse are reflections in the line Y equal X. That is, when you graph the functions on the same set of axes, their graphs are reflected in the line Y equal X. That is, the line Y equal X becomes a symmetry axis, like you would have the Y axis being a symmetry axis for an even function. So this again tells us it is convenient to use the same independent variable here so we can see this symmetry in action, so to speak. So I don't want you to think that we're just being sloppy. The idea is every 1-to-1 function implicitly defines a reverse path. X goes into Y, Y goes back into X. There's no ambiguity because all of the elements in the range are unique in the sense that once you hit a range element, that's the last time you're going to hit it. No other domain element will map into it. So again, be flexible with this, but know there are times when we're going to want to preserve the X's and the Y's or whatever letters we're using because of the context of the problem. Now, everything on here tells you all you need to know about 1-to-1 functions and inverses, and it really is pretty simple. Gosh, we could have talked about this the first day of class, but the thing is, the beauty of this is that when you take calculus, you study the calculus of inverse functions. So this is a topic that you're going to see over and over in your math classes. So what I'm just saying is let's get used to it. Now, I have an example here that I want to cover. Now, when you go through all of this, the first thing to do is to think about a simple example that's discrete, and then go to an example that utilizes a formula that you used to in college algebra. So let's start with a simple example so we can quickly move on to our quadratic friends. So let's just say that we have the following setup. That is, I'll take real simple numbers. 1, 2, 3, and 4. And we're going to define a function f that maps each of these domain elements into unique elements in the range. So I'll just say 5, 6, 7, 8. Sometimes the simplest examples make the best teachers. So this will be f. And so now what we can do, we can think of the following, that f equals all of these ordered pairs, 1, 5, 2 comma 6, 3 comma 7, and 4 comma 8. So now, again, it's one-to-one. Clearly, different inputs have different outputs. So now we can go in and say F is one-to-one. So now we can define explicitly the reverse path. Right there, F inverse. So by observation, which we don't have to do fancy equations, we see that F is indeed one-to-one. So now F inverse, we just flip these around, 5, 1. It's not always this easy with equations, but it's still the same idea. 7, 3, 6, 2, and then 8, 4. So again, we write in the inverse function just so we have a direct copy of it, but we see that this function implies this and vice versa. So we could have started with this function and say, well, it's one-to-one, so it implies the reverse path. Now, what we want to do in this particular case is just say the following. So we can write this out. So the domain of F will be what? 1, 2, 3, 4. But that is the range of F inverse. The range of F is 5, 6, 7, 8. But that's just what? The domain of F inverse, like I said before. So this is why we think now of the independent variable being the same, because now you have a path and a reverse path. You have the function F and its inverse. And so you can look at this and say, well, let's just see how these relate when we graph them on the same set of axes. So that's why I chose the easy numbers, so we can get a good picture. Not that, you know, we have to have easy numbers. It just makes it a little bit easier to graph. So I chose these nice whole numbers so we can basically have the same scale on each side, so it's easy to see the y equal x line. So we'll do the same 1 to 8 on each axis. 1, 2, 3, 4, 5, 6, 7, 8. So that takes us to 8. So 1, 2, 3, 4. And we'll do the same here. 1, 2, 3, 4, 5, 6, 7. I'll have to run up here into this. Sorry, 8. I could have shifted this down a little bit. That's okay. We'll survive. And now, so 1, 2, 3, 4. And then I'll put this in another color so you don't confuse it. There's my 8 up there. So let's go ahead and draw the line y equal x. So just pick 4, 4 if you like. So this is our symmetry line, which is just basically the definition of an inverse function. This is y equals x. So now let's just say that we will plot f with blue points and f inverse with red. So 1, 5, 1, 5. And then 5, 1. And then 2, 6. So 2, kind of eyeball it. Not going to be perfect, but it'll be fine. 2, 6. And 6, 2. Now 3, 7. So this 3 and then the 7, just kind of eyeball that. and then 7, 3. And then 4, 8 up here in the stratosphere. So 4, 8 about right here. And then 8, 4. So now when we look at this, we compare this. The distance between this point and the line y equal x equals this distance, this point in the line y equal x, by the symmetry principle. Again, our picture won't be perfect, but it will certainly illustrate if we try to make sure that the axes, you know, look right. Now, of course, if you use a different scale on the different axes, then it's a lot harder to see the symmetry. But that happens too. So indeed, when we graph F here and we graph F inverse here, we see symmetry in the line y equal x. That is, the graphs are symmetric in the line y equal x. So one determines the other. If I know F and it's 1-to-1, I can write F inverse. Now, if I have an equation, I may be able to show that it's 1-to-1, but it might be kind of difficult to actually write the, what I'm saying, it might be kind of difficult to actually write the actual formula. Sometimes it's hard to come up with a closed formula for an inverse function. And when we do the standard trig functions, we have to symbolize it because we will define them in a geometric fashion. And so when you get to calculus, you'll figure out that these functions can be written in terms of infinite series. So often the existence of an inverse function doesn't always mean that we have a nice, neat formula to write down. We know it's there and we can use it. As long as we generate points on F, we can always generate the points on the inverse function by just switching them. So the idea here, now we want to extend to a formula. So everything I've written here, we can now cast upon an actual formula equation. So we'll do that. And I've got an example here that will take us back to our transformations from the last lecture, where an imposed restriction comes from the domain. And what I've written here is f of x equals the square root of 3 minus x. Now, when you look at this particular problem, the WebAssign, they might ask, you know, is it 1-to-1? You know, can you figure out the inverse function? Things of that nature. I mean, 1-to-1's pretty straightforward. You know, if you've got a 1-to-1 function, I mean, if you verify that, that's the first thing. And then use that information to generate ranges and domains and get a graph once you figured out, you know, that information. And if possible, write down a formula for the inverse function. And that pretty much does it. So we can say, prove F is 1-to-1. Now I'm going to get lazy and I'm just going to say 1-1. You can write it out in the letters, but that's too much. Prove F is 1-to-1 and then write F inverse. So again, don't worry that you might be working a problem where a nice formula for this is not available. If you've shown that a function is 1-to-1, you know it exists. So first, what we want to do here is kind of look at this. First, let's just do some college algebra to it. The domain of F, and we're good at this, that'll just be non-negative input. So we have x such that 3 minus x is non-negative. I've gotten questions about domains of compositions. Again, please use the definition of the composition to provide the logic. Again, the logic is all there and it'll tell you exactly what to do. So that's where we have to follow the symbols. What do the symbols tell us? Well, now This just says that x must be less than or equal to 3. So we'll write that out in set notation. But then in interval notation, which again, please always follow the formatting. They will give you a picture of what they want you to type. And if they give you a parentheses or set of them, don't type parentheses again. They were already included. So be careful that you follow formatting. So negative infinity to 3 bracket. Now, we haven't proven that it's 1-to-1 yet, so I can't say range of F inverse, but we will eventually. Now, of course, the range is just the definition of the principal square root function. We know this is 0 and greater. So this is just 0 to infinity by definition of the principal square root. Now, so we look at this and say, okay, well, it looks pretty good. We'll be able to fill in these. What we need now is 1-to-1. So we're going to use the definition. So we'll just use A's and B's. F of A equal F of B. Now, again, when you think about these types of examples, it doesn't matter how you work them out. Your algebra can vary from your classmates as long as the operations are legal. So now when we look at this, we're thinking, okay, well, F of A, we just replace X with A. And now F of B, replace X with B. Now, of course, we know that the arguments, the radicals are equal if the arguments are equal. So we think about squaring, but that just means 3 minus A must equal 3 minus B. I mean, if the square roots are equal, this has to be the case. And then, of course, the 3's absorb, and we have negative A equals negative B. So now the negatives absorb, and we get A equal B. So this means F is 1-to-1. So now we can go back up here, and so that says the inverse function exists. So we can say this is the range of F inverse, and this is the domain of F inverse. So what I chose here first was to pick something we could graph because they're functions we know about. Another example will be a rational function, but we'll hold off on the graph until we review plotting the rational functions. Now, the idea here is we know we've got 1-to-1, so we know we have a reverse path, the inverse function. So let's see if we can actually write it down. So now we have y, we just call f y equals the square root of 3 minus x. So what we want to do is get that formula. This basically says you input an x and output a y. Now we want to flip that around. We want to input a y and output an x. We want the reverse. So like we did before in a problem, we want to solve for x, like I did in a previous lecture. So now in order to do that, we're going to need to square both sides. So y squared equals 3 minus x. And so now if we solve for x, we can take the x to the left and take the y squared over to the right. So this will be x equals 3 minus y squared. And so now we think about the first page of all the details. This would just symbolize f inverse of y, where we preserve the x's and the y's. Now, if our interest is plotting because this and this are the same thing. This is basically the same function. There's nothing new about this. These are just rewritten. So this says what this says. So in order to get that nice symmetry in the line y equal x, we now let f inverse of x, just for convenience, we replace the y's with x's. So we get this. So when we think of an inverse function in terms of graphing, in terms of the symmetry principle, we think this. This simply showcases this function where now the y is independent, where here the x was independent. So again, this identifies the reverse path in a way that's convenient for analysis. So if we need to analyze the reverse path, say we just started with this and that was our initial function. And now if we look up here, the domain, okay, domain of F inverse right here, this says now that X must be greater than or equal to 0. So that's restricting this. So if we had started with this, we could have ended up with this as the inverse function. So what we're seeing here is that if we look at this quadratic function with this restriction, it is 1-to-1, but that restriction is built into the fact that this domain was restricted to this. So the neat thing about this is it's all connected. We just have to decide how do we want to display the information that we have. Now, so we've got a nice function that's 1-to-1 written with the independent variable x, and we have the inverse function written with the independent variable x. So what we could do now to finish off is just plot both of them on the same set of axes to see the symmetry. Now, in order to do that, we can use the symmetry in the shape of these functions, which we already know, but let's just get some cheat points. So for instance, if we input 3 here, let's just get an x and a y-intercept. We get a 0, so this is an element of F. So equivalently, 0, 3 is an element of F inverse. Now, if you think about this, what do we get when we put in 0? What for the y-intercept? We just get square root of 3. So we're just going to get cheat points here because we're just lazy and we don't want to work too much. So this will be square root 3, comma 0, element of F inverse. So now we can plot these on the same set of axes. Again, this doesn't have to be a work of art. You just want to have a reasonable graph. And I think we, you know, our motivation is that it's neat enough so that we can see the symmetry. Now, if you want, we can go ahead and I'll do the same thing. Let's just say we do this in red and we do this one in blue. So let's start out with this one. So we have F, so what, 3, 0. I'll go ahead and mark these off. 1, 2, 3. We've got this. And then we have, let's do the same thing. We've got 0, root 3. So we'll do the same scale here. There's 1, 2. And then square root 3 is about approximately 1.7. So we'll eyeball it about right there. And so now we can go ahead and get our vertical tangent. So we'll just draw a piece of it. Again, you know, we're not going to win. Professor Ron's not going to win any art awards for this, but I'll get over it. And so now we can say, all right, well, now we want the points on F inverse. So 0, 3. So I'll go all the way up here, 1, 2, 3. So 0, 3. And then square root of 3, 0. So about 1.7 here, right there. Eyeball that. And now, of course, this will open downward. Again, we've got the negative there using our transformations. And of course, our symmetry too. So here's F inverse. So what we're seeing is that we just have a quadratic function that has been restricted because the other branch would be over here. And of course, that would not make it one-to-one. So we get this automatic restriction here that makes sure that this branch is one-to-one like the blue branch. So again, we can now look to see, and of course my picture's not the best. That should, I guess I should have done a little bit better here. Here's my symmetry line. Y equal X. So my picture is not drawn well. I drew this one a little bit too broad. So I should have come out a little bit more to bring the red curve out more. And so to have intersected a little closer to there. But like I say, this is not Rembrandt. So what we're seeing here is that we do get a symmetry and we get one-to-one functions that we can actually see when we graph with the same independent variable. So we get all this information for free. That basically, once we understand one function and it's one-to-one, we get the other one just by flipping coordinates and drawing this based on the symmetry line, or just based on the fact that we know what the curve looks like. But in a lot of cases, when we only have F, we can use this symmetry line as a gauge to figure out what the new graph should be. So whatever's over here, we think we've got this mirrors this, and this mirrors this. So this part mirrored, this part, this part. So this acts as a mirror between these two functions. Now, let's try another one. The other equation is just a rational expression, just to get a little bit more practice with this technique. So let's do x divided by x plus 4. Now, I won't graph this one until we can review the rational, but let's just go ahead and get all the interesting ideas here. You have enough on your plate right now. I keep you busy, so we'll wait till we review the asymptotes. But that won't be difficult when we go over it. That'll be a good review. But right now, I just want you to focus on the definition of one-to-one. So now what I would like to do is the same thing, prove F is one-to-one, and then write a formula for the inverse. Remember, if we have a discrete set like we had in the very first illustration, we don't have to worry about all of this algebra. It doesn't exist for that problem. So now what we want to do is first check out the domain and range. So the domain of F, of course, would include all real numbers except -4, because we know that division by 0 is undefined. And again, we'll be able to fill that in once we prove this part. And then of course the range of F, this is an example I've done many times before. We see that the ratio of leading coefficients here, the 1 will not be hit because of that 4 there. So we have to exclude 1. So that'll be a useful technique when we get back to our rational functions and we practice with the asymptotes again. So remember, when we do the one-to-one functions and their inverses, the vertical asymptotes will become horizontal and vice versa. So that'll be useful. I just think if I try to throw all of that on you right now, it's a little bit much. So let's just kind of do this sequentially and in pieces. So what we want to do now is let f of A equal f of B. Notice if I ask you to show, or a problem says, the problem might just say compute F inverse because they tell you it's one-to-one, okay? You should still be able to do this in most cases where you can actually solve the equations. So we can say A over A plus 4 equals B over B plus 4. At least now you have some way of quantifying what it means for something to be one-to-one that really is mathematically correct. So if these two are equal, we can cross multiply. A times B plus 4 equals B times A plus 4. Again, not very difficult. The more complicated the functions, the more terms we would have, clearly. So now we have AB plus 4A. And then here we have a BA, which we could write as AB. And then 4B. So now we can see the AB's absorbed. They just subtract out 4A equals 4B. And then, of course, the 4 is absorbed, and we get A equals B. So I don't think you're surprised at all that this is 1-to-1. F is 1-to-1. So now we can go back here and say this is also the range of F inverse. This is also the domain of F inverse. So they just interchange. You know range and domain of F, you automatically know the range and domain of the inverse function. They just interchange. So now we've done this part, and we did some extra here, okay? This is not as profound as the previous problem. I mean, the previous problem, the restrictions were, you know, right in our face, so to speak. So what we want to do now is come up with a way to figure this out, and we'll use the same technique we did on the last one. So we're going to say let y equal x over x plus 4. Now, we want the reverse path. This says input x and output y. Now we want to go in the reverse direction. That is, we want to input a y and output an x. So solve for x. You do not want to interchange these first. That is completely incorrect. And if you have learned that way, then unlearn it, because that does not preserve any restrictions we have on x's and y's. If you flip them around, then you flip the restrictions without even knowing it. So do not ever do that. And if you've been doing that, unlearn it. And you know me, I'm fine with you doing problems any way you want, but mathematically things have to make sense. So now we have what? Y, x plus 4, cross multiplication equals x. So now we just multiply. Well, after this is simple. Xy plus 4y equals x. So now we want to get all the x's on one side. So if you like, I don't know, we can go ahead and take all the x's over here. So we have x minus xy. It'll cut down on the number of negatives. And then, of course, the 4y is hanging out here. Now, of course, I put the x's on the right, so that seems kind of odd, but we'll survive. So now we have what? X times 1 minus y equals 4y. So now we can solve for x by dividing by 1 minus y. Of course, assuming that we have good arithmetic here. But notice, this is now F inverse of y. So this is the formula, now the reverse path. Now you put in the y and you output the x. So this is where we were with the last problem. Again, a reverse path in terms of y. Now, if we were interested in showcasing the function as an independent function with the same independent variable x, we can now let F inverse of x just flip out the y's with x's and write this way, 4x over 1 minus x. So what this does is showcase this function as an independent object. Notice these equations are equivalent. They mean the same thing. This is equivalent to this. We just solve for one variable, doesn't matter. All of these equations are equivalent. So we didn't say anything new except we solved for x. And so now we have the reverse path. But if we want to focus on the inverse function as a distinct function, then we can do this and then have the ability to plot the function and its inverse on the same set of axes. Okay, so now we're seeing that the concept of solving for one variable in terms of another and then doing the change as the last step is really the proper way to do it, so that we maintain the mathematics of our discussion. Okay, so again, it's not difficult when you think about this. It's very straightforward. Once you define a one-to-one function, you know you will define it. Then you show you have a one-to-one function. Then you have the reverse path. And in some cases, you can actually do this. In every case, it is not possible. And we will see instances of that when we study trigonometry. And that'll open the door to, like, wow, this is really just a bunch of symbols now. You've already seen this before with the exponential function and the natural log function. Those are symbols. You don't have nice formulas for them. They can be represented as infinite series, and you have to use the series to tabulate values. So there's an instance that you have already encountered. So I guess I like the trig functions because they're so useful in the calculus, but the exponential and the log are likewise useful. Okay, so that kind of beats up the one-to-one. Now, I will go back and do another illustration about the one-to-one once we get to some word problems in the quadratics. It'll make a nice transition there. So when we think about this, at this point, what we want to do is make a transition to our friends, the quadratic functions. And like I say, I found out that when I talk about a couple of examples applying the quadratic functions, it makes a nice segue to an application of an inverse function. And then, of course, it'll make a little bit more sense to you. So these are quadratic functions. Now, when we think about quadratic functions, we just basically think about the quadratic equation. So when we write a definition of this, we have what? We have the same as before, A, B, and C are real numbers. And just like with the quadratic equation, we don't have a quadratic equation if we don't have a squared term. So we must insist that A is non-zero. Okay, then we define the quadratic function. Again, you know pretty much everything I'm going to say here, but we're going to just put everything into a nice package. The quadratic function, well, I guess it would help if I spelled this right. The quadratic function, and we'll just call it f. We're so lazy, we use f of x for everything. Ax squared plus bx plus c, where c is a real number. Now, I may make the observation here on the last problem that we did, or the previous to the last, we had a restriction on the quadratic function. Note, in general, the quadratic function is not one-to-one. So we pretty much can tell how we would need to restrict the domain to make it one-to-one, but we need some more vocabulary. So that's a good thing to remember. Now, this is where students say, okay, there we go, Professor Ron, this is standard form. Well, this is one of them. If you're asked to write a quadratic function that's given to you this way in standard form, do not type this again. Obviously, there is another standard form that WebAssign wants you to use. I thought it hilarious when students would say, well, this is standard form. I said, exactly. I said, but they're not going to ask you to type what they just gave you. So let me write it this way. We'll call this the first version. I mean, I'd say, well, touche, it is a standard form, but maybe not the one we need. Here's the second version. And this version is useful. It's called the completed square version. So we'll say completed square. So it looks like this. So if you complete the square, we've been doing this, we'll do it more today. We get A, and here's the completed square part, x minus h quantity squared. So this is starting to look like a circle, but not quite, plus k. So this is the second form. Note, and there's some interesting things about this. Note we have to preserve the minus here, that's a convention, and then we have plus k. So this is like the equation of a circle where the h and k would represent the center of the circle, and then of course the r squared term would give you the radius. But in this case, we have some special names for the coordinate pair h and k. So let's write down some nice attributes. We'll say B, the point B with coordinates h, k, is the vertex, of f of x. Now, the vertex helps to define the max or minimum of the function, but I'll say more about that. So this is actually very important. So once you find the vertex, you know a lot about the quadratic function. And so if you complete the square and you make sure you have the negative here, you could read the h, which is the x coordinate, and you can read the k, which is the y coordinate. So this is very useful. 2, some students, and I don't use this as much because I like you to get practice with the completing the square technique. You can also write h in terms of the a and b here from the standard form. This will be the opposite of b divided by 2a, sort of like the quadratic formula. And then k would actually be the image of that under f of minus b divided by 2a. So these are formula alternatives. Now, like I say, most of the time we'll do this to get practice with it, but of course you might be in a physics class and your professor just uses these formulas to do. I like to show you some techniques where you can use algebra and symbolic calculation to make the work easier. We don't want to do a lot of tedious work unless it's taking us somewhere important, and then we learn something in the process. Now, the third part is this. If A is positive, that is, if this leading coefficient is positive, we already know that the function becomes arbitrarily large on either end. It tends to infinity. If this is the case, then k right here is the minimum. That is, it's an absolute, is the minimum of f. The minimum of f. And that basically means graph, which is parabolic, opens upward. This is really a conic section, but we're focusing on the functionality of it, because obviously conic sections could open right and left and they can be rotated. So this is just a special case. If A is less than 0, then K is the maximum. This occurs a lot in the applied problems. Maximum of F. That is, graph opens downward. Now, just to throw in, we know we have this U shape. The graph of F, the graph of F is a parabola. So what we're seeing is that the vertex basically defines the maximum or the minimum of the function. So when we think about here in this previous problem, even though it's truncated, right there, 0, 3 is the vertex if we extended this around. So that's really an important point in the quadratic function, even if it's restricted. And lastly, here, and this is just a little extra, x equal h, that is if we just look at the vertical line defined by the x coordinate of the vertex, is a symmetry axis, is a symmetry axis. So it's like alluding to the even function, so to speak. We think of having a parabola, the vertex, something like that. And so there's the vertex, and the symmetry axis, which is the vertical line x equal h, just divides the graph into symmetric pieces. So again, the vertex is really where lots of the interest of the function abounds. And so we might get a couple of other points, and then we can use the symmetry axis and have a very good picture of the quadratic like we did in the previous problem. So now what we're seeing is that you can actually derive formulas, like we say, we derive formulas for the h and the k by completing the square of this general equation, and that's fine. But I want to actually focus on some specific examples. So just like with the one-to-one, this kind of summarizes all of the interesting facts that you could use with the quadratic function. And of course, we could talk about other things, but this will be more than enough to get us started. So let's look at an example. Again, when you think about these problems, we introduce some techniques, and then we do the same algebra we've been doing for 20 years, so to speak. You know, if I have students that come by the office and haven't seen them in a while, I say, you haven't seen you in 50 years, and now they say that to me, and it's like back at you. But we start to learn ideas in mathematics, and we never let go of them. I mean, factoring, you know, number theory, they're here forever, and so we want to make sure that we maintain those skills when we learn new mathematics. The sad part about math in most studies is that you have to know what came before to be able to move forward. And so maybe, you know, if you all stay in your STEM careers, I'm sure you will, when you get your jobs, then you'll maintain your expertise, because your boss will want you to do that, and to move up, you'll need to do that. So we'll keep doing the same thing for the rest of our lives. So now we have f of x equals 2x squared minus 4x minus 3. Now, what I want you to do is just, let's learn everything about this. So we will complete the square, and provide a reasonable graph. Now, what they do in WebAssign is they'll say, okay, student in Professor Ron's pre-cal class, what is the vertex? What is the max or the minimum? What are the x-intercepts? What are the y-intercepts? What's the axis of symmetry? Now put that all together and sketch it, okay? So kind of dry. Now doing particular problems, maybe you might have a problem where they ask you for just a piece of that, one component. So again, don't think you have to do this every time, but I think this is a good example that kind of takes us back to our understanding of quadratics. So first, we want to complete the square. So remember, when you complete the square, you have to start out with monic. So we need to factor the 2 from the x squared and the x term. So this gives us x squared minus 2x. And then we leave some space and just throw the -3 right here. Just get it out of the way. We're not putting things on different sides of an equation now, because we don't have that luxury. We could, but don't do that. So now we're thinking, okay, so how do we complete the square? This is monic, so we take half of this coefficient, we say -2 divided by 2 and square it. Well, -2 divided by 2 is -1. That's going to go in the completed square. And when we square -1 using properties of real numbers, we get 1. Okay, so that's the so-called completing the square term. So we add this and subtract this. So we add 1 and we subtract 1. The idea is if we complete the square here, now we have again, our identity, perfect square. Then what we want to do is say, okay, that's a perfect square, but this was what we had to do to pay for it. Okay, so don't disregard this part. It's easy to leave out. Remember, and we do this in math all the time. We rewrite things. We don't change them mathematically in the sense that it's a different function. We rewrite them. So we're doing an adjustment, but the equation or function still represents the same object. Okay, so remember to not get so excited that you completed the square to forget that payment term. We have to pay for this. So now we have 2 times x minus 1 quantity squared. And then, of course, 2 times the -1, that gives us the -2 minus the 3. That's just been hanging out. So now f of x is 2 times x minus 1 quantity squared. And I'm going to say plus a -5 just to kind of, utilize the symbols I did on the second standard form. So now look, the h has the negative, the k has the plus. So this implies, or equivalently, the vertex will now be 1, -5. Okay? Now, one thing about the completed square form is that it does open the door to x-intercepts. I mean, let's face it, if we bother to complete the square, we might as well not go backwards and use the quadratic formula. That'd be a waste of time. So there's a really nice appeal to completing the square. And you really do need to be able to do it well. So don't think that I'm just doing this because, I'm being a tyrant. This is important. So now what we can do is say, okay, well, let's do a little bit of summary here. We see that a is positive. So a is greater than 0. So this implies, in this particular case, that the k, which is the -5 is the minimum of f. We get that for free because this opens upward. So this defines the smallest value of the function, and it is absolute. There is no other value of the function that meets this. So it is indeed absolute. So, okay, well, we got that for free. And now we have x equal 1, x equal h is the axis of symmetry. One nice thing about quadratic functions is that they don't change. It's the same thing every time. The coefficients change, but that's it. You do the same thing every time. The numbers can be less user-friendly, obviously. So now let's go ahead and do the intercepts, x-intercepts. Now, since we bothered, it's like, okay, since we have this, let's use it. No need to go backwards to use the quadratic formula. So now we say, in this case, 2 times x minus 1 quantity squared minus 5 equals 0. So if we want to find the x-intercepts of a function, as we see right here, we set f equal to 0. Okay, so now we can add 5 to both sides. The square root property is easy for us to use, and we have confidence with it. And now divide by 2. And now our friend square root property. Something squared equals a real number. So x minus 1 equals plus or minus the square root of 5 halves. Always write your square root property this way. Don't put a radical on each side or whatever it is some students want to do. That's not how I've taught you. We don't have to do that. The only radical is we need is right here. So if you've got this, this is the next line. I think it just makes you feel good to write it, but don't do it. Just say this implies this, and vice versa. Okay? Now you're thinking, okay, well, so how do I finish this off? Let me go ahead and do a little bit of rewriting so that our formula, our values will look nice. It's okay to have the radical downstairs. You know, I don't worry about that, but we want to make it look a little bit more convenient. So let's go ahead and rationalize. So again, root 2 times the root 2 will be 2. That's the square root of 4, which is 2. And then, of course, root 2 times root 5 is root 10. So we get the plus or minus. So now x equals 1 plus or minus root 10 over 2. And if you like, let's just go ahead and get a common denominator of 2. So we get 2 plus or minus root 10. Now, the thing is that our intercepts aren't really nice, but that's okay. We can estimate their value. We have an exact copy of them. And one thing I'll show you sometimes is that, for instance, if we just want a cheap estimate, let's just say that we take square root of 10 to be approximately 3.2. That's an overestimate, but that's okay. We'll survive. And so now we're thinking, okay, so we have 2 plus root 10 over 2, just so we can get a nice little ballpark figure. This will be approximately 2 plus 3.2 divided by 2. So this will be 5.2 divided by 2. So 2 into 5, that'll go 2 times 12, so 0.6. So that there's just a rough estimate of that. That's all we need for the graph. We're not doing a fancy calculation with the Google calculator. We're just getting a roundabout value like I do in some of the Smart Pen videos. And now, what about 2 minus root 10 over 2? We could estimate this differently, but let's just go ahead and work it out. So we have 2 minus 3.2 over 2. And again, when you think about this, this is based on the axis of symmetry. So I could use the axis of symmetry to get this value here, and I'll remind you of that. So again, when we look here, this is going to give us what? A negative 1.2. And we divide by 2, so that'll be a negative 0.6. So now what we're thinking is that if we've got these intercepts, if we take the midpoint of the intercepts, we should get the h. But since we're kind of guesstimating, we're not really using that. But the intercepts, actually, when we can get nice copies of them, we can take the midpoint of that segment to find the actual h of the vertex. So that will be another way to find the vertex without having to do so much work. So there's a different way to do everything. Now, okay, well, what's the last piece of the puzzle? The y-intercept is easy. Just replace x with 0 and we get negative 3. So for y-intercept, we have negative 3. Okay, so let's get our inexpensive graph. Usually I say provide a cheap graph of this function. So let's do it. Again, we're not trying to win an art contest clearly, but we want it to be reasonable. The hardest thing is to make sure that the axes have good scales on them so that things come out okay. You know, a lot of times when you sketch things, you overdo some things, so don't worry about that. Notice here we have 1, negative 5, so we'll spread this out a little bit. 1, and then 1, 2, 3, 4, 5. Not much room there, Professor Ron, but this is the minimum, so I'm okay. There's my vertex. And then now we'll go with the 2.6. So 1, 2, 3, about right here. And then we'll go with the negative. So 1, 2, right here. And then we can dot in the axis of symmetry. Which is x equal 1. And now we've got a vertex and 2 points, and then we will also have the -3, right? Right there. So we got more than enough detail to get a fairly good graph. So let's go ahead and sketch it in. We know it's parabolic. And then we can sketch in the other side. Okay, so now, again, we're not looking to win the art contest, but now we see that we have the vertex 1, -5. And then we can go ahead and map in these numbers exactly. This will be 2 plus √10 over 2. We have our -3. We've already marked our axis of symmetry. And here we have 2 minus √10 over 2. So the idea here is we just want to have a reasonable graph. And so we see that this is more than enough information to have a sufficient graph. And often a visual is good if you're doing a presentation. And now you can say, okay, the vertex is really the key to making a quadratic function one-to-one. But I mean, you can restrict a function however you want. You could start here and go on. That is, you could start at this number and let x go to infinity, and that piece is one-to-one. Okay? But if you want a real inexpensive way to do it, is you can use the vertex to get more value for the dollar, so to speak. So if we say x is greater than or equal to 1 for our f, we go here and we just take this branch, we have f is 1-to-1. So WebAssign might say, well, which restriction makes the function 1-to-1? Your choice. Now, of course, now here we could say if x runs, x is less than or equal to 1 or -infinity to 1, that's also 1-to-1. So we could say 1 f x less than or equal to 1, f is 1-to-1. So that would just be this branch here. And then you can think like vertical line test. But the nice thing, horizontal line test, but that's only because we've done all the work here. Because the shape or the actual shape of the graph is parabolic, we understand that. And that gives us plenty of flexibility. But you could section this, either of these branches any way you want and get a nice one-to-one function. So don't think this is magic at all. This is simply, of your choosing. So WebAssign will just say, they may give you a couple of restrictions and say, pick one which makes f 1-to-1. And you probably will have already computed the vertex. And so you can just say, okay, well, that one's right, but that one doesn't make any sense or whatever. So restricting a domain to make a function 1-to-1 is a common technique in mathematics. So embrace it. We will do it in trigonometry. We don't necessarily have to do it with the natural log and the exponential, because the natural log starts out by definition 1-to-1 when we get to calculus. So certain things are given to us on the silver platter. We just don't have to work very hard, and we won't have any disagreement with that. Now, again, when you think about what we do mathematically, you might say, okay, well, can we take this newfound understanding of the quadratic function and make something more of it? Does this help us if we're working with quadratic functions? Clearly, the answer is yes. So let's look at a couple of examples with this. Then we'll head back, do a couple of these, then we'll say a little bit about that inverse function. So what we have here from your WebAssign, we did a profit equation or inequality in 1.8. So I thought this would be good to kind of bring us back into that domain. We have R of X, and I want to show you a new technique, is 80X minus 2/5 X squared. Now, what we're going to see is R is going to represent a revenue function. We'll say where R is a revenue function, in dollars. And X represents the number of units produced. So again, the quadratic function is very useful in business analysis. The natural exponential is very useful too. To say that the quadratic function is important is an understatement. So what I want to do is show you a technique. So you might say, okay, Professor Ron, I have an observation here. That's a quadratic function. It has a squared term and a linear term, but it doesn't have a constant term. So what I might ask you in this case is, what is the maximum revenue? And then we say, how many units must be produced? Now, the thing about this type of problem is, if you recognize what kind of function you have initially, then the problem is straightforward. But if you read this and say, well, I'm not in calculus, I can't do this. Well, we don't need calculus for this. This is one problem where we can optimize a function without the use of calculus. When you get to calculus, you can verify all of this by derivatives. But if you recognize that this is quadratic, then these two questions are fine. That is, the K from the vertex gives you the maximum. And of course, the H that provides that, or the X that provides that, is the H. So we just need the vertex, basically. So we think of the geometry of the quadratic function as opening the door to its optimization qualities, so to speak. So let's do it. Now I want to show you a factoring trick that will make this easier. Now notice there's no constant term. So we see that 0 is an easy intercept. So let's factor this. Because there's no constant term, we don't have to work as hard, and we don't have to even, work up a square. We don't have to complete the square. We don't do minus b over 2a. We just cheat. And let me show you the method. So note, new technique, that is no constant term. So when we don't have a constant term, that opens the door to a new way to do this. So R of X equals negative 2/5 X squared plus 80X. And I've taught you how to factor, so we'll factor symbolically, and we'll factor the negative 2/5 and the X out of both of these terms. So we can get monic. Monic is always easier. One of the factors is monic. It's much easier. So now we just leave an x here. That's the easy part. So with this particular part, we can say plus -5/2. This is an easy way to counteract the -2/5 without having to do it in your head and making mistakes. So now notice we factor the x, but now we have to counter the -2/5 by a -5/2. That's 1, and then of course the 80. So we get the 80x that we need here. So again, we have rewritten. We have not changed the function. So now let's finish. -2/5 x. So now we have x. Now, of course, we'll just divide the 2 into the 80 to give us 40. So we have -5 times 40. And that just gives us a 200. So -2/5 x times x minus 200. Now, when you look at this, we can easily compute the other intercept. That's why we factored it. We know 1 is 0. We can see that from the very beginning. And that's why these make really good production models in economics. So now we say this equals 0 if and only if x equals 0 or x equals 200. Now, like I said before, we can bisect the interval created by the x-intercepts because we know that x equal h is the axis of symmetry. And so these would be displaced equidistantly on either side of that axis. So we just do the MP, the midpoint. The midpoint will be 0 plus 200 divided by 2. So that's just 200 over 2, which is 100. But now that's good because, again, the axis of symmetry, this is h. Now, of course, you can do minus b over 2a, and that's fine. There's nothing wrong with that. But I want you to get used to this because this is a good presentation technique. We have a curve that's opening downward. And so now we have the value of the x coordinate of the vertex. And now notice, because we bothered to factor this, this makes a real easy evaluation. This is r of x, but in a form that's easy to evaluate. That's a messy thing. We could factor the x, but this is like really easy. So now K, if we want the maximum revenue, we know we need 100 units. We have R of 100. So we'll just say 100 units. So now we can substitute here -2/5 times 100. And then with the symbolic computation, this is easy, 100 minus 200. So now, of course, these are easy numbers. 5 divides 100 20 times. So we get -2 times 20. And of course, 100 minus 200, we can do that in our head as a -100. So this gives us a -40 times a -100, which will give us what? -4,000. So we see max revenue of 4,000 100 units produced. So what I wanted to show you here is you can actually do the minus b over 2a and knock this problem out really quickly. But I think when you look at it that way, you're like, okay, well, I can just run the numbers and I'm fine and I'm done with this, and you learned about that much. If you now look at this problem as a simpler algebraic entity because of the lack of the constant term, you can look at this problem in a way that takes you back to the 0 product law. And the zero product will then showcase the axis of symmetry, that is, the midpoint of this segment created by the x-intercepts gives you the what? X coordinate of the vertex. And then the simple presentation you have here for R makes for simple evaluation. Okay, so when we're evaluating polynomials, we often want to try to factor them somewhat because, or use synthetic division, because it's a pain. It's really difficult to raise numbers to higher and higher powers. And we struggle with that because we want to be able to compute, but we want it to be accurate. So we don't want to take so many shortcuts and make mistakes, and then we can't even check our work. At least here, if we are careful about our algebra, we produce something that is useful and user-friendly. So think about it this way. Taking an opportunity to make an observation about a quadratic function opens the door to other insights. Now, of course, you may see other things in a problem, but they're not terribly interesting, nor are they very efficient. But when it comes to doing the calculus, efficient is not always open to us. We don't do busy work, mind you. We don't just do work to do work. We do the work that's necessary to do the problem correctly. And there is a big difference. So now I have an example here. Again, I pulled these from the WebAssign. And I changed the way I wrote it, that WebAssign wrote it, just to kind of vary it a little bit. Back when I was an undergraduate at Carolina, I got to teach some business calculus as an undergraduate. Well, I just said that. And so I taught a class in intermediate algebra, I taught a trig class, and I taught a business calculus class. And when I taught the business calculus, I made up a problem like this, but I made it harder. And one of the grad students said, "Oh, these students are cursing you, Ron. This is a hard problem." I said, "Well, our advisor asked us to make up questions for the final. And so we did what we were told because we wanted a paycheck." So he said, "Oh, well, good for you, but they will not like you when they figured out you made up the problem." So that brings back a lot. So the example here will be, this is another production type model. It says if N trees, N is the variable, N trees are planted. If N trees are planted per acre, then, so per acre, this is important, per acre, then the tree produces, that is, the trees on the acre produces this many apples, 1,870 minus 17 N apples. So you look at this and say, well, okay, you know, N's too big, then starts to drop off. So the idea here is we want to be able to work this problem, hopefully as a quadratic. Maybe it will turn out that the quadratic function is what ensues here. Then the next thing that Professor Ron wrote, it says, write a formula A of N that represents the number of apples produced per acre. So write a formula A of N that represents, or just say representing, we overuse the word that. We all do. I'm bad at that, right? Write a formula representing the number of apples produced per acre. And then what we want to do is maximize A, and then also compute number of apples. So if we want to maximize A, we want to find the optimum number of apples that each tree should produce, and then figure out what the actual money is going to be, or actually the output is going to be. So we're going to do the same thing we did for the last one. Now, of course, if this gives you the output per tree, then we need to multiply this by the number of trees per acre. So that's the easy part. You're thinking I made such a difficult question out of this. It's not hard. So A sub n will just be n times the output per tree, because we want to write a formula that represents the number of apples produced per acre. So here's our quadratic, and you're thinking, that's even better than the last problem, because at least it's factored somewhat. So we'll just say quadratic function. So the idea here is that you might be doing a model in an economics class that's similar to this, and you will utilize your understanding of the quadratic function to optimize it. There are all kinds of nice problems that can be written this way, and we could spend a lot of time on it, but you know, we just want to get the basics down here, and then allow you to be able to expand upon this as you need to in your future courses. So now we're going to note again that this is factored. It does have a 0 when n is 0. So we're going to do the same factoring process and do the midpoint. So now A of n, I'm going to turn this around, negative 17n plus 1870. So notice with the last problem, we had the n multiplied. So now we just want to factor the negative 17. So negative 17n will give us here an n, the n's already factored, and then this will be plus 1870 divided by negative 17. So we just want to compensate for multiplying the 1870 by negative 17. So the same song and dance, it's easy, it's just doing the same procedure. And so now we've got good numbers here. So 17, I put the minus here, 17 into 18 will go one time. Then we have another 17, which is 1, and then a 0. So that was easy arithmetic. So at least this is not like the time break distance problem with the horrible least common denominator that was just, you know, I'm thinking, web assigned, why are you doing this to us? So now notice, if we set this to 0, we can see that now we have the actual intercepts, the one to join the 0. If and only if n equals 0 or n equals 110. All right, so if you compare this to the last one, we've done exactly the same thing. So now midpoint will now be 0 plus 110 over 2, which is 110 over 2, which gives us what? 55. So this says we need 55 apples per tree. So we need 55 apples produced per tree. So the idea here is, when you think about it, so 55 apples. Give me a second here. We're going to figure out the apples. We need to plant. Sorry, that's the number of trees. We need to plant 55 trees per acre. Sorry. The math always corrects you. So now this is the n. N is the number of trees per acre. So if we're interested in maximizing, and that's what I said, actually here, that's what I should have said, compute n. We're going to compute the number of apples. That's what the A is going to be, but compute number of trees. this will give us the number of apples. I mean, I was really trying to tie this into the end, not that. We know what that is. That represents the number of apples per acre, but we want the number of trees. So go ahead and make that change in your notes. So now we're seeing for optimum production purposes that we need to focus on approximately 55 trees per acre. So again, you don't know this unless you do the mathematics. Again, you don't want so many trees on the acreage that they choke each other out clearly, but then you don't want so much space between the trees that you lose money because you just didn't plant enough. So what you want to do is do a model and work with a mathematician, work with an ecologist, and decide, well, based on the biology of the land where you plant, what would be the best for your conditions. So again, there's a whole lot going into this. I mean, when these formulas are developed for a realistic situation, it's important that there's a lot of work done. You don't just make it up, but the mathematics we need to do, I'm sharing with you now. So now this implies, well, of course, we're going to be lazy. Let's go right up here. Here's our formula for A of N. So now we need A of 55. And we'll do some symbolic computation here. So this will be negative 17 times 55, and then 55 minus 110. So we have negative 17 times 55, and of course, 55 minus 110, we know what that is. That's negative 55. So the negatives absorb, and we get 17 times 55 squared. Now you're thinking, okay, that's kind of a hard number to estimate, and we want an exact number. So now we can use symbolic computation. So here's what we're going to do. We're going to break this up into two pieces. 17 is 10 plus 7. So we're going to do 10, and we're going to write 55 as 50 plus 5 to do more symbolic computation. Maybe after this, you'll understand what I mean by this, and we square that. So we're going to use the binomial identity plus 7 times 50 plus 5, quantity squared. So it's easy to multiply by 10, and it's easy to multiply by 7 because it doesn't have extra digits. So now we have 10, and then of course, what goes in both of these is the same thing. I could have factored it, but it's a little bit easier to take care of it if you separate it. So we've got what, 50 squared, that's easy, that's 2,500. And then we have 5 times 50, that's 250, times 2 is 500. So we write it out so the numbers are easy. And then of course, 5 squared is 25. So now do the same thing here, just be a court reporter. We have 7, so we have 2,500 plus 500 plus 25. So now we can go ahead and combine the terms. We know what they are. This will be a 525, so we get 10, 2,500 plus 525, same thing, plus 7, 2,500 plus 525. And now these are easy to add. So we have 10, so we've got a 25, and then 5 and 5 will give us a 0 with a 1, so that's 3,025. And same here. So this is what I do when I do symbolic computation, especially with the mixture problems, the time, rate, distance, and the fraction of work. You will never have any success with those types of problems if you don't change your approach to where you can do it in a symbolic calculation type. Get rid of the decimals and let the algebra do the work. That way you can actually check your work and know that you did it correctly. So now we're in good shape. 10 times anything just means adding a 0. So 30,250. And then let's multiply by 7. So that's a 5 with a 3. So that's a 17 with a 1 and then a 21. So 21,175. So let's add these up. So we get a 5, and then we get a 7 and a 5, that's a 12. And then a 1, so that'll give us a 4. And then a 1 and a 5. So we get 51,425 apples. So, you know, like I said before, we get really involved in the mathematics. So let's just again look at this and say, okay, we have the existence of a quadratic function. So this one is even more so useful for this technique. It's factored pretty much, except for that part in which we cleaned up. And so don't go backwards, go forwards. So now if we factor it and take the midpoint of the x-intercepts, then we get the h. So I can just go ahead and add h. And then of course here, if you like, let me put a little space here. This is just the vertex. So this implies that k is a of 55. So when we look at this, it's the same as the last problem. We take advantage of the algebra. We take advantage of the lack of a constant term, okay? So again, as you're working your problems, you can mix and match. You can substitute numbers into a formula. You don't need me for that. You need me for techniques that you haven't seen before. And so again, think about this and try different approaches. If you just need to find the max or the minimum of a quadratic function, try the formulas. Or, okay, I'm going to complete the square. Oh, there's no quadratic term, or excuse me, there's no constant term. I'm going to do the midpoint technique. Remember, the minimum or the maximum is the value of k. So it's going to take more work. To get k, you have to find h. If you complete the square, you get the h and the k for free. So you're really finding both. So basically, however you approach it, the h is going to come out in the wash. So to get the k, you've got to either get the h and the k through completing the square or utilize the technique that I have here. So again, you have plenty of opportunities to utilize whatever technique you want. Now, what is a good technique? I mean, when you think about it, what is a good technique? Well, in my book, a good technique is a technique you know how to do. So if you study consistently, then you can use whatever technique that comes to you when you read the question on test day. And you're like, well, I can do it that way. I can do it that way. What decisions. So what I want to impress upon you is that when you test, you want to be in a situation where you're like, man, I'm so glad to be done with this test. I'm tired of this work. I'm ready to move on. That's what I want for you. So the consistent work that I'm seeing is really going to pay off highly for you all when you test. Now, what I wanted to do is just go back and do a quick review of one of these inverse problems. Now, the problem up here was in one of the one-to-one functions that actually you ended up with the golden ratio, and I decided that this is kind of theory of equations, so I didn't do it. It'll be a good example later, but I decided to do the one where the quadratic and the square root actually cross in a way that's simple. These overlap in a very non-simple way, and so I thought I'll just leave that one out and talk about it later. If you remember synthetic division, that's what that is. So a lot of times I'll say, okay, well, I'll save that to when we've developed our expertise a little better. Now, what I wanted to do is just go back and make a comment about an inverse function. This is a lot simpler than the quadratic function, so I thought it'd be a good one to end with. Now, when you look in 2.8, which is the one-to-one, there's a problem, Marcello's Pizza. And this is what I was talking about keeping the letters preserved. Very simple, but very important. So this will be good for you. Marcello has the following hypotheses for his pizza. He charges $19 for a large pizza and $1.50 for each additional topping. Okay, that's some good pizza. You know, pizza's good. It's filling, but when you're hungry, a good pizza is excellent, and it's kind of like having gourmet French fries or whatever. If they're not hot and warm from the oven, you got to do it that way. You know, you come home from Whataburger and you put the fries in the oven to make them crispy and delicious. So pizza's the same way. So of course I'm making everybody hungry. I'm
No.
sorry, forgive me. That was bad. -10 for me. Okay, so now, oh man, I'm ready for a double meat Whataburger. Okay, I'll be quiet. Now it says we need a function that models the price of a pizza with n toppings. Okay, so if we have additional toppings, that means n is greater than or equal to 1. So we have the fixed cost of $19 plus 3/2 times n. So that's easy. Okay, so I wanted you to see this at work when it's really simple. Now notice, tell me something. Is this function right here, y equal 19 plus 3/2 n, is that 1-to-1? It obviously looks like it's 1-to-1. Is it 1-to-1? Let's prove it, because I obviously assumed it was, but let me just prove it and then we'll be done. So look here. We have f of n equals 19 plus 3/2 n, okay? So we'll say f of A equals f of B. So that means replace n with A. So we have 19 plus 3/2 n, A equals 19 plus 3/2 B. Now, of course, the 19's absorbed. I'll move this up. So that gives us 3/2 A equals 3/2 B. Now, of course, the 3/2 absorb, and we get A equals B. So this implies what? F is 1-to-1. So, but again, now you're thinking, how simple is this? Now, so I didn't prove that here, but I thought, okay, by now they'll believe me. And so now the second part of the question says compute F inverse. Okay, so if we set y equal to 19 plus 3/2 n, then we can do what? Solve for n. So right here, just like we've done before, we now need to have the input y and output the number of toppings. So solve, or additional toppings, solve for n. So we subtract 19 from both sides, and then we have that equals 3/2 n. So now multiply by 2/3 to absorb the 3/2. So we have n equals 2/3 times y minus 19. So this is the number of toppings on the pizza that costs y dollars. So if you think of variables y and n, then this setting is better for the problem, because now this makes perfect sense. Y is the cost of the pizza. You can input the y and then figure out how many extra toppings the customer had on their pizza. Now, like I said before, maybe you want to graph the function and its inverse on the same axes. So you're thinking, okay, I'm just going to switch all of these out to n, so you could write the inverse function this way. But for graphing purposes, this is fine. But for understanding purposes, this is like what you do in science. If you do Fahrenheit and centigrade, the same thing is going on. You want to preserve the letters so that you know what they mean. So for instance, in a science class, you may stop here because again, you know, n is the number of additional toppings and y would be the cost of the pizza. And that's going to make more sense. So you might be checking the receipts at the end of the day and you want to compute this. Maybe your manager needs to know this. maybe it's written on the receipt. Maybe it's not. Maybe he figured out you're taking Professor Ron's pre-cal course and he knows you could do it. Well, whatever the case, this is under your control. When you work out these problems, if you're graphing, then it's good to go to this point. But if you're just looking for a formula that writes n as a function of y, where n and y have specific definitions, then it's fine to stop here. So we write the inverse function in terms of y. And that's what I'm trying to talk about here. So when you think, let me go back to that original sheet. I can find it. The idea is when we complete our work, I've got it right here. That's quadratic. Give me a second, I'll find it. Got to go through all the stacks here. Oh, here we go. Remember, on the very first page, we had this. That is, you can choose to write your inverse function in terms of the variable y and preserve this, like we just did in the problem about the pizza. But like I said before, the convenience of using the same independent variable is apparent when we want to graph the function and its inverse on the same set of axes. So in order to preserve the symmetry in the line y equal x, we utilize that technique. I don't want you to think that you know, we're just being careless, but sometimes it's important to showcase the inverse function as a unique unit. And so we do this where we replace the independent variable in the first calculation here with the independent variable here so that they're aligned. So when we graph them, x is independent for both functions. And that's when we see the nice symmetry property that we have here. That is, when we're interested in seeing how the graphs are symmetric relative to the line y equal x, that's important. So I want you to see the distinction. Unfortunately, in college algebra, you go through this rather quickly, and that may not be apparent, but hopefully today, as you start working on your WebAssign in one-to-one functions and quadratic, all of this will kind of come together and assimilate, and you'll have a better understanding. Okay, well, I'm sorry about the allusions to food. Now that we're all hungry, maybe you all can take a break and go grab a hamburger or something, or take a nap, which I'm sure you deserve. Thanks for your attendance today. I hope that you are working hard. I know a lot of you are. Continue to work and know that the rewards will be huge when you take your test. Everyone have a good day.
You too.
Thank you, bye.
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 Have a good one.
Thank you. Bye.
Thank you. Have a good day. Yeah, I like the comments. Those are good. LOL. Yeah.